Good morning, everyone. So today let us discuss with 8051 interfacing and its application with different interfacing concepts. So till now we are discussed within the last class about LCD, interfacing with LCD, interfacing with LEDs. So in this today's class we were discussing about interfacing with DAC, interfacing with stepper motor. Okay, so let us start with the things. Yeah. So 8051 interfacing temperature sensor. So here we are using LM35 or LM34. So here we are going to interface the temperature sensor with 8051 microcontroller, and we know that this temperature sensor, so what we are going to use here, uh, here we are measuring the room temperature. So we are converting that analog to digital form, and then only the microcontroller will understand the value of temperature. Then we are going to use. In this session, I will also show the application of this particular experiment, how it can be used as a project. Okay. So the temperature is converted to electrical signal using a transducer called as a thermistor. In the last my session, I told that. So all the electrical quantities or signals are converted to electrical signals using transducers. So transducer is the main thing here. So it is very simple and widely used temperature sensor, which is that LM35 or 34, which is Semiconductor Corporation. And this LM34 does not require any external calibrations since it is internally calibrated. That means it's not required any calibration done externally. It can collect the temperature value and it can calculate it, and it can give the value. So this LM34, 35 are precision integrated circuits. These are precision integrated circuit temperature sensor whose output values, that is voltages, is linearly proportional to Celsius temperature. It does not require again external calibrations since it is internally calibrated. This is also same thing as in 34, and the outputs will be 30 millivolts for each degree of centigrade temperatures. So this LM35 is a widely used temperature sensors. Okay. So next, how it is going to happen? What is the procedure or the flow it is going to take place? There is signaling conditions. So here it is a flow chart. What I have shown here. First, it is going to check the analog data. That is analog word we call from the external source. It may be a temperature or pressure, whatever it is. Then the output of that analog data is given or fed to the transducer. We may call it as a sensor. Then we have to do signaling conditioning. After doing signaling conditioning, we have to give it to analog to digital converter. After converting that analog signal to digital, we need to give that data to the microcontroller for take the necessary action. This is how the actually flow is going to take place. The sensor produces the output in the form of voltage, current, and charges, resistance, and capacitance. So these are the output forms of sensors. It may be different also than this. So these are some of the forms. But we need to convert these signals to voltage in order to send input to ADC. That is, ADC is analog to digital converter. This conversion is called as signal conditioning. Okay. So as I told in the flow chart, here what we do is the sensors which have the output forms, that is voltage, current, charges, resistance and capacitance, these are converted into signals. In order to convert these signals to the voltage, in order to send it to the ADC, that is analog to digital converter. This conversion is called as signal conditioning. The signal conditioning can be current to voltage, the conversion, or signal amplification. It can be a current to voltage or signal amplification process. So how we can connect the LM35 to analog to digital converter? In this slide we are going to learn which are the pins, how and all. The temperature versus voltage for ADC, that is analog to digital converter. This is a table. Here we have the temperature. Here we are having input voltages in millivolts. These are the output voltages, and we are converted this into binary form. That is D0 to D7. Since we know that in the last class we learned this ADC, what we are using for interfacing with 8051 is a 8-bit ADC. The resolution with max of 256 steps. It is having a resolution maximum of 256 steps, and the LM35 produces 10 millivolts for every degree of temperature change. That means if there is any temperature change, for every degree it is going to produce 10 millivolts. We can condition the input voltage of ADC to produce Vout of 2.56 volts, okay, for full scale output. So V reference is equal to 2.56. So the reference voltage will be 2.56. Okay, ready? So the reference voltage will be 2.56 volts. So we can condition the Vin of ADC to produce the output voltage of 2.56 volts for full scale of output. Okay. So let us say the temperature is 0 and the input voltage is 0, and Vout will be all zeros. So if the temperature is 1, if the Vin is 10, Vout will be 1. In a similar fashion, if you check, if the temperature is 30 Celsius, the input voltage will be 300 millivolts, and the Vout will be, you can see, 1E. Okay, like this. So next, so this in this diagram we are showing here how the microcontroller 8051 is interfaced with ADC. It is analog to digital converter. So here we have port 2. So port 2 and port 1 both we are using for interfacing our 8051 to analog to digital converter. This LM35 is your temperature sensor which is connected to channel 2, and the voltage for ADC as well as microcontroller we are given 5 volts. Here it is grounded, and this one the V reference we are giving to part of 10K. Okay, so this is how the pins are interfaced with the microcontroller to ADC, then to LM35, that is temperature sensor. So now before going to the next one, that is 8051 interfacing with DAC, so let us learn uh, how it can be used for doing any small projects. So here a digital thermometer using LM35 and a microcontroller. So this is a diagram how it can look. So in Google, if you can get lot of data regarding this, if you just search like interfacing stepper motor, interfacing the DAC, interfacing the temperature sensor LM35, like this, if you type, you will get lot of links, out of which, so here you can see this is microcontroller 8051, this is LCD display, this is a pot. Okay, here they are connected in temperature sensor. So here it is temperature sensor, they made a connection. So this is ADC. So now you can see the components required is 8051 board, ADC board, LCD display, temperature, potentiometer, and jumper wires they are taken. So this is the software implementation, how they are implemented microcontroller, LCD display, temperature sensor, ADC. Okay, this is how actually the interconnections of each 4 pins will happen. This is the pin reset pin, and here measuring the temperature, how it is going to take place. It is 8-bit microcontroller window, which is having 128 bits of RAM. So next, so this is a block diagram. So microcontroller, it can give the data, it can take the data. So it is bidirectional, ADC 0804, and this is single direction, that is LM35. The temperature sensor will sense the temperature and it will give to ADC, and this ADC will convert analog signal to digital signal, that is using signal conditioning, what we discussed in the slides. So then that input will be given to microcontroller, then will be programmed to display the data in the LCD screen, that is going to happen. So here we are using 16x2 LCD, that is liquid crystal display, what we discussed in the last class. So these are related to LCD. Okay, so these are related to ADC. These are the control pins to display and all. So this is for ADC data. So temperature sensor. So let us concentrate on temperature sensor. So here the output voltage is linearly proportional to Celsius voltage, and this comes ready with calibrators. As I told, it comes ready with calibration. It will calibrate automatically. Its output voltage is 10 millivolts. Okay, which produces a voltage corresponding to temperature. and the voltage is converted to digital, that is 0 to 256 by ADC, and it is fed to a microcontroller. Got it? That means what temperature it is going to send, that will be converted to digital in the form of 0 to 256, that is decimal, that is fed to temperature. Then this temperature is converted to ASCII form, which will be suitable for display, which will be on 16 cross 2 LCD display. This is the actual output what you can get. Regarding code, so regarding the code, what the code we are using in the lab, same code you can use, the same anyway I explained in the lab, so that you can refer, okay, for coding purpose, that is interfacing of temperature sensor with microcontroller. Okay, here we are using um, C language. In our lab we are used assembly language. Okay, now you can see how it is going to get the output. So as I told, this is LCD display, this is a microcontroller, this is a pot, this is ADC, and here we have the temperature. Now you just see the switch on the circuit, so just observe the video. So how to get the output here in this, so have a look towards LCD display. This is ADC, and we know the operating voltage of microcontroller is 5 volts. See, now we can see the temperature display, that is temperature 26 degrees Celsius. Okay, like this we are going to display the temperature. Okay, now let us continue with the 8051 interfacing with the DAC, that is digital to analog converter. Till now we discussed in temperature sensor, that is how we are going to convert analog signal to digital signal by using ADC. So in this experiment we are converting a digital to analog conversion. So digital data what we are giving in PC, that we are going to convert in analog. That will I'll show how we are going to do this. So the microcontrollers are used in wide variety of applications, like measuring control of physical quantities like temperature, pressure, speed and distance. In these systems, the microcontroller generates the output which is in the form of digital. As we know that microcontroller is widely used, and many a times we are going to generate an output from the microcontroller in the form of digital. But in order to control some of the system, we need the signal to be converted into digital form. So in that reason we are going to use this DAC to interface with 8051, which is going to convert this digital data into analog, which is equivalent analog voltage. So we'll make use of digital to analog converter, which is a device which is used to convert digital pulses to analog signals. So in the next figure we are going to show that it is a 8-bit DAC which is of 0808. It is a number, model number. In this IC, which we are going to convert a digital data into equivalent analog current, hence we require so input to voltage converter to convert this current into equivalent voltage. That means current to voltage converter we are going to do. So we are going to get an equivalent voltage. So DAC 0808, which provides 256 discrete voltage or current levels of an output. That means what digital data you are going to fed, it's going to convert it into analog form. Okay. Next. So DAC 0808. In this microcontroller, in this DAC 0808, the digital inputs are converted to current, that is I output, and by connecting the resistor to the I output, we convert the result to voltage. The total current provided by the I/O pin is a function of the binary number of D0 to D7 inputs. A DAC 0808 and the reference current, that is I reference, is as follows. So now we have D out is a least significant bit, D7 is a most significant bit for an input, and reference voltage is of input current that must be applied to the pin number 14. So I reference current is generally set to 2 milliamps. Okay, that's how actually DAC is going to work. So if you take the equation for output voltage, we'll take reference voltage into D0 by 2, D plus D1 by 4 plus D2 by 8 plus D3 by 8, 16 plus D4 by 32 plus D5 by 64 plus D6 by 128 plus D7 by 256. For example, if the data is 0, 0, then the V reference is 10 volts. What happens? 10 into 0 by 2, 0 by 4, 0 by 8 like that. So the output voltage will be 0. Okay. If the data is 80H, then the V reference is 10H. What happens? See here. So it is 0.5. So 10 means 5. So the output voltage will be 5 volts if the data is 80H. Okay. Next. Interfacing diagram of DAC with microcontroller. This is 8051 microcontroller. This is a DAC. So we are connecting pin number 1.0 to pin number 1.7 to DAC D0 to D7. Okay, this is read write. This is 5 volts VCC, and this is grounded the reference. Okay, so it is an amplifier which we are to scope means we are connecting to CRO to see the output. Using DAC, we can able to construct triangular wave, square wave, sine wave, sawtooth wave, okay, ramp wave, etc. So like that. Only thing is we need to code accordingly. So next is actually stepper motor interfacing. So before going to this, let us discuss the applications of this, how we are going to do. Okay, interfacing of DAC with 8051 microcontroller. Okay, in this section we are seeing a DAC which is using 8051 microcontroller. This is a device which is used to convert digital signal to analog signal, as I told already. And there are two methods of converting digital signal to analog signal. These two methods are binary weighted methods and R2R ladder methods. So majorly they are going to convert DAC, that is digital to analog conversion, in two methods. One is binary weighted method, another one is R2R ladder method. So kindly remember in this article, so here we are going to study about this. The chip uses R2R ladder method. This method can achieve a much higher degree of precision. A DAC are judged by its resolution, the resolution of the function of the number of binary inputs. Here we are taking an input as 8, 10, 12, etc. like that, and we are going to find the discrete voltage levels, and the same formula what I told in the PPT. Correct, no? The same thing. So we are going to generate a sine wave using DAC. So here we are going to give the angles like this 0. So sine theta, V out will be in the form of voltage. If you convert that values in the form of decimal, you will get these values, that is 128, so 192, 138. So with respect to this, we see the angles. So from 0 to 360 degree, you will having these many data. Initially, it will increase. See here, 128, 190, 192, 238 like that. 198, 128, 198, 238, 256. So 238, 292, 188. Okay, like that. It will increase, decrease. Fine. It is like that. Here to here it is for positive cycle, here to here for negative cycle. So this is the exact implementation of DAC microcontroller. So DAC, so this is the amplifier, this is the output which is fed to CRO. The same program which we are using in our lab, same thing you can have a look. Same actually the video already I shared. So as I given in the above, see here the values are being kept as an array. So in order to construct like this, see, sine wave. So since it's a digital to analog converter, we need to give a digital data. It will be converted into analog form. So we'll get a smooth curve of sine wave. Okay. Fine. So now let us discuss about 8051 interfacing with stepper motor. So in the video what we shared with the lab, if you refer that you will understand clearly how actually the stepper motor interface will be done in practical manner. So here in this diagram you can see we have four magnets. So we call it as A, B, C and D. So here you can see the rotation of motor which will be in clockwise direction, which we have shown. This is just for your understanding we made. So the stepper motor is widely used device to translate the electrical pulses into mechanical movements, and the stepper motor is used for some of the applications like disk drive, dot matrix printers, robotics, like this. So see, these are some of the applications. In the Viva they may ask you these questions: what is stepper motor, what are the applications of it, like that. So the stepper motors are commonly have a permanent magnet, which we call it as a permanent rotor, or a shaft, which is surrounded by a stator, as I shown in this diagram. So we have four magnets. So next, the commonly used stepper motors are four stator windings, which are paired with the center tapped common. Such motors are called as four-phase or unipolar motors. So here you can see the single shaft. So here are four magnets. So here what they do is stator motor. So we call it as A, B, C, D. So this is how it's clockwise. If it is rotated like this, this is a anti-clockwise. So a practical PM temperature, that is stepper motor, will have 1.8 degrees stepping angle and 50 tooths on its rotor. So practically if you think the stepper motor, it will be of 1.8 degrees of step angle and it is having 50 tooths, and these are 8 main poles to the stator, and each is having 5 tooths in the pole face. So it is the first magnet what we have shown in the diagram. So here you can see the motor start rotating, and I told it is a clockwise 1, 2, 3, 4. So it will start rotate like that. See, you can see the color code also. You are going to energize the coil. That how the motor is going to rotate. Okay. So four step sequence we are going to do. So first, in the first step, what we do is winding A will give it as 1, winding B 0, 0 and 1. Then in second condition we make 1, 1, 0, 0. In third condition 0, 1, 1, 0. Fourth condition 0, 0, 1, 1. To the windings. For clockwise direction, what we are going to do? 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 1. For anti-clockwise direction, we will go reverse. 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1. This is for clockwise. This is for anti-clockwise. So step angles. This step angles is defined as minimum degree of rotation associated with single step. The total number of steps needed to rotate a 360 degree is step per revolution, and the number of step per revolution is given by 360 degree by step angle, and each step per second, which is given by RPM. So we know that we are going to measure the motor speed in terms of RPM. RPM into steps per revolution divided by 60. For example, if the step angle is 2 degree, so the number of steps per revolution will be 180 degree. Okay, like that. So this is the interfacing diagram of a stepper motor with a microcontroller. So this is a microcontroller. So 89C51. So it is a port 1 we are using. 4 ports we used. So line driver we will call. So this is the driver IC for driving the motor. We will use ULN 2003 for driving the stepper motor. Use one power supply for motor and ULN driver, and another for 8051. So unipolar stepper motor. So we are having 4 coils as I told, and we are going to use 5 volts power supply. So next is interfacing of keyboard. Before going to this, let us discuss about practical applications of it. Yeah. Stepper motors using 8051 microcontroller. So here, as I already told, what is a stepper motor and what is this ULN 2003. ULN 2003 is a driver, motor driver. So to drive the motor, this is a circuit diagram. how we are going to use. This is a LCD display, microcontroller. This is a stepper motor. This is a motor driver. These are the components which we are required. Same code you can refer for what we are using for lab. So this is C code, but where you are done in assembly language. So you can see the working, how it is going to rotate. See, it is rotating clockwise, running forward, running backward means anti-clockwise. So here in this diagram you can see this is LCD display and microcontroller board. So these are LEDs, these are keyboards, and this is stepper motor, and this is stepper motor driver. Okay, so we are going to give a power supply of 5 volts of adapter, and it's going to work, and the code is dumped into the microcontroller. That how actually the process is going to work. The working circuit is very simple. The method is called off stepping is implemented in the program, which is using a stepper motor. When the forward button is pushed, the stepper motor rotates clockwise. If the reverse button is pushed, backward button is pushed, it starts rotating anti-clockwise. To stop the rotation completely, you can press the stop button. That means they are programmed in such a way that each button, the stepper motor is going to perform the specific operation. So this is a circuit diagram, microcontroller, stepper motor driver, stepper motor. So you can see this video, how it is going to done. This is a liquid crystal display. So they are using a capacitor with a resistive load of 10 kilo. So that is a motor. You are going to dump the program, and you are going to execute. So the motor starts rotating. The motor will be driven by this stepper, this motor driver IC. This is how it is going to work. These are the steps. Initially, it switch on the circuit. Microcontroller start driving the stepper motor. One can observe that the rotation is the stepper motor. The stepper motor has a 4 wires. They are yellow, blue, red, and white, and these are energized alternatively, as we have discussed before. So how we are going to energize, depending on that, the direction of the motor will be decided for positive cycle or negative for clockwise or negative anti-clockwise direction, depending on that, which I shown in the presentation. Okay, so these are the applications. It can be used in robotics, mechatronics. It can be used for disk drives and matrix printers like this. Okay, kindly refer this textbook. It is very good for both like instruction set, interfacing, everything. That is Mohammad Ali Mazdi, the 8051 microcontroller and embedded system using assembly and C. So same book I referred. It is very good book. So kindly refer this book for any further clarification if you want. So there are a lot of examples, programming examples also. So it is very easy to understand. Both C and assembly language both are there. So go through this.